This is day 12 of Advent of Cyber 2024, and this challenge is called If I Can't Steal Their Money, I'll Steal Their Joy. Werewolves Bank had a huge turnover this year and expected massive profit before the holiday season. They were eager to disclose this news to the townspeople during the Stockholm celebrations. However, to their surprise, things went the other way around. After completing the annual calculations, the accountants were shocked to see a considerable loss. They observed discrepancies in the account balances. The bank called McSkitty to help investigate these users' fraudulent transactions. Upon analysing the bank's website transactional logs, McSkitty found some interesting transactions. Few users, including the mayor's team, initiated multiple transactions from Werewolves reserve accounts at once. Surprisingly, all these transactions succeeded despite exceeding the user's current balance. Glitch was already aware of the critical vulnerability, allowing these fraudulent transactions. The mayor malware and his alliances exploited. So the learning objectives for this one are to understand the concepts of race condition vulnerabilities, identify the gaps introduced by HTTP2, exploit race conditions in a controlled environment, and learn how to fix the race. So we need to turn on the virtual machine and the attack box. So web timing and race conditions. Conventional web applications are relatively easy to understand, identify, and exploit. If there is an issue in the code of the web application, we can force the web application to perform an unintended action by sending specific inputs. These are easy to understand because there is usually a direct relationship between the input and output. We get bad output when we send bad data, indicating a vulnerability. But what if we can find vulnerabilities using only good data? What if it isn't about the data but how we send it? This is where web timing and race conditions attack come into play. Let's dive into this crazy world and often hidden attack surface. In its simplest form, a web timing attack means we glean information from a web application by reviewing how long it takes to process our requests. By making tiny changes in what we send or how we send it and observing the response time, we can access information we are not authorized to have. Race conditions are a subset of web timing attacks that are even more special. With a race condition attack, we are no longer simply looking to gain access to information, but can cause the web application to perform unintended actions on our behalf. Web timing vulnerabilities can be incredibly subtle. Based on the following research, response time differences ranging from 1300 milliseconds to 5 nanoseconds have been used to stage attacks. Because of their subtle nature, they can also be hard to detect and often require a wide range of testing techniques. However, with the increase of adoption of HTTP2, they've become a bit easier to find and exploit. The rise of HTTP2. HTTP2 was created as a major update for HTTP, the protocol used for the web applications. While most web applications still use HTTP 1.1, there's been a steady increase in the adoption of HTTP2, as it is faster, better for web performance, and has several features that elevate the limitations of HTTP 1.1. However, if implemented incorrectly, some of these new features can be exploited by threat actors using new techniques. A key difference in web timing attacks between HTTP 1.1 and 2 is that 2 supports a feature called single packet multi-requests. Network latency, the amount of time it takes for the request to reach the web server, made it difficult to identify web timing issues. It was hard to know whether the time differences was due to a web timing vulnerability or simply a network latency difference. However, with single packet multi-requests, we can stack multiple requests in the same TCP packet, eliminating network latency from the equation, meaning the differences can be attributed to different processing times for the requests. This is explained more in the animation. So instead of just sending one, you can run a request, you can send two, and see the timing differences between both of them, which indicates how much time was spent processing the first and then the second. So with network latency a thing of the past, only server latency remains, making it significantly easier to detect timing issues and exploit them to recover sensitive information. So typical timing attacks. Timing attacks can often be divided into two main categories: information disclosures. Leveraging the differences in response delays, a threat actor can uncover information they should not have access to. For example, timing differences can be used to enumerate the usernames of an application, making it easier to stage a password guessing attack and gain access to accounts. Race conditions. Race conditions are similar to business logic flaws in that a threat actor can cause the application to perform unintended actions. However, the issue's root cause is how the application processes requests, making it possible to cause the race condition. So for example, if we send the same coupon request several times simultaneously, it might be possible to apply it more than once. For the rest of the task, we'll focus on race conditions. We'll take a look at time of check to time of use flaw. So let's use an example to explain this as shown in the animation. So we're sending request to the server, but what's happening is request 1, submit discount. Both of them was the code activated, false, and then as they're running at the same time, it would apply it. But with this one, if you have them run one at a time, the first one would apply the coupon, and the second one wouldn't. When the user submits their coupon, in the actual code of the web application, at some point we perform a check that the coupon is valid and hasn't been used before. We apply the discount and only then do we update the coupon code to indicate that has already been used. In this example, between our check if the coupon is valid and our update of the coupon being used, there are a couple of milliseconds where we apply the coupon. While this might seem small, if a threat actor can send 2 requests so close in line, it might happen that before the coupon is updated in request 1, it has already been checked in request 2, meaning that both requests will apply the coupon. Winning the race. Now that you understand basic concepts related to race conditions, let's explore how this vulnerability occurs in the real world. So for this, we will need the web browser, and we'll also need Burp Suite. Actually, we don't need the web browser because you can open up the browser from Burp Suite. So when that browser opens up, the Firefox one, probably exit from that, and just stick to Burp Suite. So intercepting the request. Before we start intercepting requests, we need to configure the environment so that, as a pen tester, all web traffic from our browser is routed through Burp Suite. This allows us to see and manipulate the requests as we browse. We'll use Burp Suite, a powerful web vulnerability scanner, to intercept and modify requests for this exploitation. You can access Burp Suite in the text box. On the desktop of the text box, you'll see a Burp Suite icon as shown below. Right there. One thing I'll do first is copy this and have it in the clipboard. Okay, that didn't seem to work. Let's try again. There we go. And we've now got Burp Suite open. So we will go to Next. We then start Burp Suite. And once it's started, see on the main interface that has different tabs such as Proxy, Intruder, Repeater, and others. Inside Burp Suite, click the Settings tab at the top right. You'll see Burp's browser options available. Then under Tools, enable Burp's browser to run without a sandbox option. So we go Settings, Tools, and then it's Burp's browser, and allow Burp's browser to run without a sandbox. So we've done that, then we exit from the settings. And after allowing the browser to run without a sandbox, we would now be able to start the pre-configured Burp Suite proxy. Open the browser by clicking Open Browser located on Proxy Intercept. So there should be Open Browser right there. But first thing that we should do, turn Intercept off for now, just so we can have the page load. Okay, so now with the web page open, we access the website that's on the virtual machine for this challenge, and we're now at a login page. Application scanning. As a penetration tester, one key step in identifying race conditions is to validate functions involving multiple transactions or operations that interact with the shared resources, such as transferring funds between accounts, reading and writing to a database, updating balances inconsistently, etc. So for this example, we'll log into the banking with these credentials, so 111 tester, and we can see a balance of 1000. So there are 2 functionalities to log out, and the main one, the fund transfer, which includes deducting funds from the account and adding them to other account. As a pen tester, this could be an opportunity for an attack. We'll see in detail how, as a pen tester, you can test exploit the vulnerability. So if we were to select this account and do 500, we'll see we have successfully transferred it. But now let's go to Burp Suite and take a look at the request which was made to perform this transaction. So proxy, HTTP history, and then /transfer. And we can see here, this is where we specify what account and how much. So what we're going to do now is select this request, and we will send it to Repeater, which will then allow us to make that same exact request again. So place the mouse inside the request, inside the Repeater tab in Burp Suite, and press Ctrl R. And it wants us to do this 10 times. So with that, we have 10 requests ready. We want to send them simultaneously, while one option is to manually click the send button in each tab individually. We aim to send them all in parallel. To do this, click the plus icon next to request 10 and select create group. So create tab group, and it wants a school of funds, and we add all of them to that same group. So create that. Now we are ready to launch multiple copies of our HTTP post request simultaneously to exploit the race condition vulnerability. So select send group in parallel in the drop down next to send. Once selected, the send button will change to send group parallel. So if we do this, send group in parallel, button has now changed, and once all the requests have been sent, so we need to click it now, and it has done them all. So we go back to our browser and refresh the page, and we see we have now negative 4,500. By duplicating 10 requests and sending them in parallel, we are instructing the machine to make 10 simultaneous requests, each deducting 500 from the tester account and sending it to account 111. In our correctly implemented system, the application should have preceded the first request, locked the database, and preceded the remaining requests individually. However, due to the race condition, the application handles these requests abruptly, resulting in a negative balance in the tester account, an inflated balance in account 11. So verifying the source code. Suppose you are a penetration tester with access to application's source code. In that case, you can identify potential race condition vulnerabilities through a code review. By analyzing the code, you can pinpoint areas where multiple database operations are performed without proper transaction handling. Below is the Python code that handles the transfer. In the above, if user balance is greater than the amount, the application first updates the recipient's balance with the command, and then updates the sender's, and commits again. Since these requests are committed separately and not part of a single atomic request, there's no locking or proper synchronization between these operations. The lack of a transaction or locking mechanism makes the code vulnerable to race conditions, as concurrent requests could interfere with the balance updates. So, time for some action. Now that you understand the vulnerability, can you assist Glitch in validating it using the account number 101 and password glitch? Attempt to exploit the vulnerability by transferring over 2000 from his account to the account number 111. So if we log out 101 and glitch, so if we go back to Burp Suite, by transferring over 2000, we can do, actually, firstly, we need to remove all these repeaters. So the repeater we have here has the cookies of the previous account. So what we would need to do, we'll do 111 and we'll do 500 again. So we've done that, we go back to Burp Suite and we do the same thing, going to proxy, finding the latest transfer, that looks correct. We then do send to repeater, go to repeater and do the same thing of Control R, so we'll do for them. We will create the group, we'll just keep it group 2, don't need to name it. Add them all, change to send in parallel, and send it. So now if we go back to here and refresh, we have a negative balance, and we've also got a flag. So, fixing the race. The developer did not properly handle concurrent requests in the bank's application, leading to a race condition vulnerability during transfers. When multiple requests were sent in parallel, each deducting and transferring funds, the application processed them simultaneously, without ensuring proper synchronization. This resulted in inconsistent account balances, such as negative balances in the sender's account and excess funds in the recipient's account. Here are some of the preventative measures to fix the race. Use atomic transfers. The developer should have implemented atomic database transactions to ensure that all steps of a fund transfer, deducting and crediting balances, are performed as a single unit. This would ensure that either all steps of the transaction succeed or none do, preventing partial updates that could lead to an inconsistent state. Implement mutex locks. By using mutex locks, the developer could have ensured that only one thread accesses the shared resource, such as the account balance, at a time. This would prevent multiple requests from interfering with each other during concurrent transactions. Apply rate limiting. The developer should have implemented rate limiting on critical functions like fund transfers and withdrawals. This would limit the number of requests processed within a specific time frame, reducing the risk and abuse through rapid, repeated requests. So after completing the exercise, you'll be required to go to the dashboard to get the flag, which we already did. So we will now copy it, paste it in, and that is all the questions answered. So if you like this video, make sure to like and subscribe.